Okay, now I get to try and make a comeback, going down in flames over the radiation analysis. So ironically, I think I had the right stuff up there. I just so exhausted and I didn't practice ahead of time. So looking at the manual, and so we're talking about the 1 over r squared law. And incidentally, I don't know, I think I didn't go over this, but the r squared rule basically is because if you think of, oops, got to turn on the tablet here. So you have like area of a circle, the circumference of a circle, and then you go to the area of a sphere and the, whatchamacallit, the volume of a sphere. So you may remember that the area of a sphere, surface area, equals 4 pi r squared. So that means that if I have something like a point charge, like you learned in the beginning of the semester, let's see if I can, here it is. You can say, if I make a sphere around the point charge, I can walk around on the surface, and I have a certain amount of strength of an electric field, and it has to be spread out all over that surface. That's why we get 1 over r squared, because it keeps, as we get further away, we have to spread it out more and more. So in our case, we don't know an exact formula like we would know for a point charge, but what happens is that the radioactive source, even though we have it in this plastic holder that has this sort of window in it, it still radiates in all directions, just like a point charge. So even though we're only getting a small fraction of it, the part that comes out still obeys. It still spreads out, just like a point charge, because all we're doing is, we're just taking a small part of what's coming out of it. So it still obeys the 1 over r squared. Oh, and I drew all that off the screen that you can't even see it. Hold on. I have a really big monitor, so I have the recording only a part of it, so you can easily see it on your screens at home. So what I was just drawing is right here. I've got the source and a holder, but the source basically radiates everywhere, and we're just taking a bit of it, so it radiates evenly in all directions. So that's why it's valid to say a surface of a sphere. And we'll get this back in place, ready to go. Excuse me. Where is my manual? We don't know the exact form of it, but we can set up this kind of ratio. And so by making a cross, if I cross multiply, I1 d1 squared equals to factors, and I2 d2 squared also equals to factors, and then I can set them equal to each other. Or I can just say that the factors cross out here. So we can, well, yeah, you can make them 1, but it's the same thing. Then if you solve it so it equals 1, and then you say 1 equals 1, each of them they equal each other. All right, so then one thing we could do is this business about this here, which to me is just dumb. I don't know. It's kind of interesting, but the more interesting thing, instead of doing something like that, is to do this logarithm. And the idea is then, at the end of the day, we're going to find out the p. I'm going to pause this for a moment just to make sure I'm saying it right. All right, so I mean, and when I see this exponent here, and okay, it's supposed to be squared, right? But and it's over here. But what we want to do is we'd like to see if it's really true. So we set it to be a variable now, and then we, as usual, we want to make it a straight line fit instead of fitting to something raised to a power. So then we think of using log and not natural logarithm, log base 10. It's just a little easier because you get graph paper, and we've done it before, I think. But there is graph paper available because we used to do this with pencil and ruler. So anyways, at the end of the day, I1 is the intensity at the start. So this is a constant. P log D1 is also a constant. So then if we plot log of I2 on the y-axis and log of D2 on the x-axis, we should see a slope that should be equal to negative P. Okay, so let's take a look at what we did here. So I have a distance, and there's log of distance. I have a rate at each one, my plus rate, and I need to get a plus. I take the log of the rate, and I got plus minus the log of the rate, and we went over that. And what's interesting in here, notice there's a natural logarithm down here. Oh, so here is the formula, and it's the one here, sigma f here. And we, as usual, we find a formula that fits. So we see it, we think we like this one here, which is exactly right. And then we just have to plug in which one is which. So A is the rate, sigma A is the plus minus of the rate, F is the log of the rate. And so you go through and you can come up with the plus minus of the log of the rate. So I'll let that sit there a moment so you can see it. All right. So let's see now. The distance, right, so I didn't put error bars on this. Anyways, let's see what do we got here now. So, fit line formula, it's pretty simple. The y-intercept, though, don't forget, is a composite number, which is log of I1 plus P log of D1. Over here is the y-intercept, and the slope is going to be P. And the way we've got it set up, it's not going to be negative P, it's just going to be P. Give me a minute. Oh yeah, no, it is negative P, because P is a positive number at the end of the day. Okay, so I haven't put the error bars here, but I have used them here because they don't change a whole lot. But to be fair, to do everything by the P's and Q's, we got it going on. And so we have now, let's take a look at this one here. Let's get this out of the way. So this is minus. Why do we see minus here? Hold on, because it's logarithm, right? So we're having log of I2. So I1 is one measurement, right? That's the rate at the first one, but I2 is different each time. Right? Okay. So let's see. What is it that we're actually plotting up here? Yeah, I want to pause one more time. All right, so yeah, this thing needs some more work in the sense that there's no axis labels here. But because we have a distances that are less than 1, because remember it's in meters, then the log of a number less than 1 is going to be a negative number. Excuse me. And so you see as it grows, it becomes less negative. So you see negative 1 all the way, up to negative 0.3. Now I suppose what we want to do here is we probably want to put a 0 there, because we want to see the y-intercept. And interestingly, we don't need to worry about, we're not going to use that as part of the residuals. And there's the fit line. I wonder if that appeared when I added that number. No, that's suspicious. Let me hit enter here. So fit line. Oh yeah, 1.886 rounded off is 1.89, as I see here. Okay. Well, I'm just a little suspicious that let's put a 1 there and see what happens. Didn't change. I don't like that. What is this using? It's using H10. So let's just do a fill handle here just to make absolute. Aha! Okay. Interesting mundo. So I'm a little concerned here that why does this thing, let's pause. Alrighty, I just did a little tweaking. So now the x-axis actually doesn't go. It goes from -1 to almost 0. You can't put a 0 in there. It freaks. So I just made it -0.0001, and it rounds it off there. What's important is that solver still gets what it needs, and I'll leave it to you guys to double check that this is correct. It's easy enough. You take the log of the I intensity 1, which is here, 3.77, and then you multiply it by the slope times the log of the first distance, which is -1 right here, and see if you come up with 1.88. But in any event, there is our fit. It looks like I have error bars on here. You just can't see it. So 1.93. I'm surprised that, well, it's 10%. It's not. It's less than 10%. Of course, you can find out what is the plus minus on that by simply adjusting the slope and watching what happens to the sum of the chi-square. Okie dokie. There you go.